Hey everyone, welcome to the stream. All right. So, quick recap. 2 nights ago, I finished implementing support for displaying structs. Let me see here. What was I doing? Yeah, this is not the example that I wanted to show, but more like this one here. So basically we have, this is just a simple example where we have a struct bar and a struct foo. Foo is actually made up of a whole bunch of members, and one of them is a bar. And oh yeah, that's it. What I worked on last stream was adding support for pointer members in structs. So yeah, this one here, this is basically the gist of it here. So if I hit F5 or not, just give me a second here. Make sure my latest build is built here. Okay, here we go. All right, so up here you can see F, which is our struct type. Type foo, actually, we should be able to see that here. There you go, foo. We've got our bar, we can expand that. It's got values as we populate it. It sets the values. And then here's the part that we got working last time. So we've got a pointer here that points to the address of F, and sure enough, it shows the value 12, and if we set through the pointer, it changes both these to 13, and that's pretty much it. So what I was thinking of working on tonight is this here. Basically add support for self-referential types, so pointers to the same type struct. So like here, you know, like a foo, like a linked list of types. And so this doesn't work out of the box. I think I actually, yeah, let me go back to my example here. So I'll remove all this. And I was also checking because I think this is related to doing support for forward declarations. Is this the, yeah, so in here I have the node and I have this forward declaration stuff. So basically I have this little macro to toggle on and off. So if do forward declaration, I forward declare this struct called forward. Otherwise I actually define it completely. Here I have a bar which contains a pointer of type forward. And of course if and if I'm doing the forward declaration, I define it below where it's, you know, used here. So forward declared here, a pointer to the type is used here, and the definition is below. And this, I was doing this because I wanted to see how it changes the generation of type information in the debug info. So if I look at here, all right, so like in the case of forward declaration, if we look here, we can see that here's bar, right? So bar is of type 25. It is equal to a struct. It's 2 bytes in size, which makes sense. It's got a member named forward. And actually this here, I wouldn't even be able to parse this currently because it says basically it's of type 26. So 26 is going to be the type of this pointer, and it's equal to a pointer of type 27. And the thing is that type 27 hasn't been even defined yet. And actually this is extra equals XS forward, which I guess, I have to look this up in the documentation, but I'm actually going to guess that this means it's like a cross reference to some type that is not yet defined. That's my guess here. Not sure it really matters, to be honest. What's funny too is that there's this extra colon at the end. So yeah, I'm going to look up what this means. I mean, I think what it means is it's telling us that, you know, we can see here the capital forward here. So probably it's saying X, my guess is X is like cross-reference or forward reference to a struct that's named forward. And then this colon, not sure. So fair enough. I don't know how important that's going to be to me yet. I think I'm going to pretty much ignore it for forward declarations. But the point is that you can see that lower down here is when we define forward. So later on, and you can see that this has the type number 27, which is what this is a pointer of. So for forward declarations, I have a problem where right now all my code assumes that types are defined in the debug info before they're ever referenced. And for the most part, that's true, except for the case of forward declarations. And in a similar way, if you look at node over here, so node is a struct that has a member of type node star, right? So this is very common. We do this all the time in C++ or C even for building like linked lists. So here you can see node is being defined as a type, number 28. It is a struct that is of 2 bytes as well. It has a member called next, which is itself a new type, a pointer type of with type 29, and it is a pointer to type 28. And this 28 here is the type that we're in the process of defining. So this is where I mean that it's a self-referential, because it's almost like the forward declare type. We're going to meet a type that has not yet been defined. And I believe that my solution to make this work is going to be the same in both cases. So that's what I'd like to do tonight. And I have this idea of how to do it. I don't know if it's going to work. Just give me a sec. Just 1 second. All right. Yeah, so I have this idea. We'll see if it works, but before I get to that, I wanted to continue sort of what I was doing last time, which is doing some refactoring of this code here. I did a nice job of removing a lot of functions that were lambdas, and now they've become proper functions. I want to just continue that because I think it's going to make a lot of this code nicer to read, cleaner and all that. So I'm not going to do too much. I think mainly what I'll do is when I have something like a stab string match, this will just call a function to handle the stab string match. So let's see what that's going to look like, especially given that these types are going to be forward declared. I just want to make sure there won't be any problem with that. Oh, and also, if they are forward declared, then I don't think I can keep them in this anonymous namespace anymore. So, yeah, that's a bit of a shame, but I think it's okay. I'll live with that. So let's see here. Guess we'll put it down here. So I'll go like. All right, now we make the match here. So ostensibly I should be able to move all this info between these two braces here right into that function. Let's see what that looks like. Oh yes, and then there's a problem of the state. I might actually change this because I'm not getting much use out of this state thing with the source file. So let's see. Okay, so I think I can remove these members here. Oh wait, no, sorry, not like that. This member here can go. I'm going to change this like this. Okay, so now I've got this one big function for this guy. What's the problem? Yes, so this is the problem I was saying before, that this struct here is not, it's an anonymous namespace. So let's see if I just move all of this out for now. Maybe I'll stick these into their own header or something. We'll see. Whoops. That was not what I wanted. Like this. And let's put it here. Okay, so now it's happy. Yeah, so that's the only part that's a bit unfortunate, is I cannot forward declare a type that is in an anonymous namespace, which is really a shame. Right? You cannot, yeah. Indeed. That's what I thought. That's all right. In the name of keeping the code clean, I think it's okay. So we do this here. Similarly, we'll have a handle stab.match. Oh yeah, this has that problem of changing the state. That's unfortunate. The reason why I didn't want to mess around with the state is just because I didn't feel like moving the state into the header as well. Maybe I should. Otherwise, is there a way for me to do this? Let me see. And here, don't I mess with the state? So right now my whole state machine is local to this one function. Whoops. Yeah, even here. I suppose one thing I could do here is, or I guess I could, for now, not have this function because anyway it's so small. So I don't know if this is going to be useful. Okay, let's say I don't do it. I just want to see what this one. This one's much, well, not much, a little bit bigger. This one here should be okay, I think. So let's see. RSD parser. Okay, that looks pretty good. So yeah, the only downside here is my inability to manage state for this guy, so I can't really have this thing. The only alternative is for me to actually move my little state machine out, which really wouldn't be a huge deal, I suppose. Guess if I do that, I can bring back my source file being part of the state. Oops, sorry about that. Alternatively, I suppose what I could do here is if I move into a function is return something that says we're done in this state. Yeah, that's what I can do. I'll leave it alone for now, and I'll put a little to-do. Okay, you know what? Let's see what it would look like if I just move this. Don't have to be too worried about all of this. So let's see. So if I did that, then I could bring this back in. Okay, well, this obviously looks a lot cleaner than before. We're doing parsing directives. We're handling the different ones. It is a little bit ugly that I don't have the state being set in one place, but it's all right. We will rename this guy, though, to have the m underscore for my members. I did it again. It's real strange how the rename renames everything except for where I just told it to rename. And I suppose at that point, don't need these either. That looks nice and clean. That's true. No need for that, since it has no members anyway. All right. This is simple enough that there's no need for me to factor it out. So now the next one that's a little bit big is this handle stab string match. So I could actually pare this one down a little further. You can see it's quite a long function here, lots of nesting. So the way to break this one down would be to have like more functions for handling each type of symbol. So one for function names, one for local variables. Yeah. this comes back to what I was saying last stream, where I have now this sort of a duplication where, you can see here for struct members, we do the same kind of matching to see if the member of the struct is a pointer as we do for like regular local variables. And the only difference really, like if I actually clean up these names and stuff, is that in both cases what we do is we do add an indirect type here. We do all this is the same all the way up until the point where we add an indirect type. So this is pretty much the same here. And then the only difference is that in this case we add a variable with that type, and over here we add a member. Or we're in the process of adding a member, and we're going to set the type here. So I suppose what I could do is I could create a function for just this portion. You know what I mean? So it'd be like, yeah, the handle elsem pointer match would be for taking it and adding an indirect type, but not necessarily adding a variable. And then I wonder if that's what I should be doing for everything else. But then for most other things, yeah, maybe it's just for types, adding types. But that's almost the only one, I think, that has this situation. Yeah. Okay, so I'll wait on that. But what I will do, since I've done this now, I can do a little bit more cleanup here. Let me just make sure this looks like still doing the right thing. Wait, did it fail? Oh, something went wrong. Okay, so let's try and see what's going on here. Danger of refactoring. Oh, there we go. Something wrong here. What's the problem? Unexpected match from member. Oh yes, all right. Huh, that's cool. Yeah, it's because of my forward declaration that I'm not handling. Okay, so this would have happened even before my refactor. So let me bring back the do forward decl back to 0 here. That's what we're going to try and get done today. So now this should work. And there we go. See, there's no local variables for these because I don't handle correctly the self-referential types. I'm not really gaining much here. Having these names made a lot of sense when I did not have these structs that actually put the same name in the functions. So now they're not necessary. So I prefer to compress my code rather than needlessly give names to everything. Although here type name I think is nice just because I use it so often. So maybe I'll keep that one. Maybe type def ID. I do use it a lot. All right, so now these types here. In fact, I only have those 3 that need to be forward declared. All right. Yeah, I'm happier with this because it'll make it easier for me, because that function was getting much too long and nested, the parse function. All right, so rst parser, refactor, or code. Refactor, I'll say refactor parse into more functions. Okay, so now that I have this, the next thing to do is to attack this forward declare thing. In fact, I'll start with the self-referential because it'll be, I think, some kind of special case of that. So let's. So here's what I'm thinking. So right now, what's happening is I can actually set a breakpoint where the problem occurs. We're going to be parsing the type node, and when we get to this guy here. So when we get to the pointer in node, we're going to say, I can't find this type. So that should be right in struct type definitions. And in here in particular, it's this guy here. So we're going to do a pointer match, and we're going to fail to find the type. So I'm going to put a breakpoint here. Hit a 5, and it's the first hit because it's the only pointer we have right now in my program. So here we go. So if we look, there's our, is this the right one? Or am I hitting forward? I guess I'm hitting forward. Oh, but in this case, it's not actually a forward. So it won't be the first one. This one's going to be found, no problem. It's going to be the second one. So here it is, next. So you see how next is a pointer of type 28. So it's going to say, all right. It's going to say, can I find type? No, it's empty, and therefore I just return silently. Well, not silently because I actually logged that I couldn't find the type. Show that here. Because here, like, warning, type not found for next, type not found for N3, N2, N1. That's all related to node. So because I was not able to fully parse node, these guys here are considered undefined. Because basically, as soon as I have a member I don't know, I just return and I stop trying to build. I guess I don't actually have to do that. I suppose I could skip this member and then continue adding other members. I suppose that would be possible. Like instead of return here, if I was to do like a continue, just to see what we should see now is that. Okay, let me just build this. I think what we're going to see is we're going to see an empty type for. So first, it's not going to keep talking to myself here. Okay. Sorry for the mumbling. Let's just see what happens here. So I come in here. So there you go. So you have nodes, but you see they expand to nothing, which is weird, right? It's really weird. But it means like if I were to add, I don't know, another property, like an int in there, we would see A, but we wouldn't see next. See, we see A, but we don't see the next in there. So I don't know, maybe that's good because at least we're doing a best effort to try to display as much as possible. So yeah, maybe we'll go with that. I'll just put a little note here. Skip this member. But the point now is actually for us not to skip this member, and the way we're going to do that is in my find type. This is what I'm thinking. Instead of warning that a type hasn't been found, I want to create some kind of proxy type, one that I add to an array, and for the type ref ID here. So every time I see one, I'm going to create this proxy type that we will then add to this array. And then afterwards, when we finally get, like when we add that type, we resolve and go and fix up all the previous types that were unresolved. So we call it, say, an unresolved type, and we will resolve it. So that's sort of what I'm thinking here. And I'm actually thinking I might be able to do it within the type system rather than like hacking it. So let's see. If I had to do that, so all these places where I do an add type, I think I would make a function to add the type so that I could do the resolve in there. So something along the lines of, we have a find type, oh, one thing with that, well, maybe it's okay. We'll do add type. And then whenever we add a type, what do we do here? We should do a bunch of stuff. We always do the same thing. So it actually makes sense for me to put this in a function anyway. All this is repeated. Type ID to type. That's good. So I need the type to find the type def ID, and I need the type itself. And I guess I will return the set type, just so that this, although here the type will be a more specific one, so maybe I won't do that. All right, so let's do this here. And I think that's the last one. Yeah. Okay, so now we have a, okay, well, this is going to be type here. Great. So now that I have those two functions, I can do what I was thinking. So the idea here would be we would look, and if we don't find the type, rather than complain about it, we would like to create some kind of a proxy. And it would look something like how would it work again? Make a proxy object. Yeah, the problem is that I don't see us assigning it here. So maybe I just return it here, and then when we assign it, oh yeah, maybe this won't work as elegantly as I was thinking. Let me think here. We do add primitive type. Oh, maybe it's okay. I'm not sure anymore. How do I do this again? We find. Yeah, so I'll have problems like here where we create an indirect type out of this pointer type. If that's a proxy, we end up storing this in this indirect type. So I was imagining that I could go and replace all the proxies, but I won't actually know where they are. Let me see. And I suppose we don't really want to add the proxy here till it's been resolved, but these guys may end up, all my variables and then my certain types of mine might have these in there. I was just having this thought about how it's kind of interesting to think like, initially when I did this type stuff, it was not polymorphic. I was trying to do this using a variant, and then the idea would be that we have this variant, of all these types, and if one of those variants was a proxy type, then that type could be actually replaced with any other variant. That's kind of interesting. It's almost like because it's an in-memory replacement. But the problem with polymorphic pointers, which is what I'm ending up with here, is I can't just replace the object in memory. All these things point to them, and I would have to go and replace all the pointers, which is really it's pain. Yeah, maybe not as simple as I thought. The only alternative I can see is I do the proxy thing, and then at the end, when I'm done, I can go through my debug symbols and iterate across or maybe add a function here that's like resolve proxy types or something, and then it goes and says, okay, well, I have a whole bunch of types here, go through my types, and any one of those types that has a proxy, replace it with the object that now, the type that actually represents it now. So I could maybe do that there. And then the other place would be, where are my variables? Oh yeah, scopes. That's right. So I would have to go through scopes as well. So that means going through my functions. So yeah, iterate through all the functions again in here. So go through all my functions here, grab all their scopes, go through all of their variables and replace those as well. So that could be done, I suppose. And then how would I replace them again? I suppose I'd have to store a ID in the proxies and then look up the type. Yeah, that's how I'd have to do it. Another problem I can foresee is this here. When I add indirect type, I actually immediately give it a name by taking the name of the type. But if the type here is a proxy, this is not going to work. That's pretty much the only place actually where I access the type itself. Normally I don't do this. I just yeah. An alternative to this would be to make it a function, and then you call it. It would ask its type for its name, and of course that would cascade. So that would delay the setting of the name, or the this whole problem with the name being set immediately. Okay. Let's just see where this goes. I'll start implementing it. We'll see where it takes me. You know, if it doesn't work out, it doesn't work out. So I'm going to call it an unresolved type. And I'm going to put here some kind of ID. All right, and then we're going to go to our find type. I think I might have to add a constructor there. Yeah. Or I can keep doing what I'm doing, which is not, let's do this differently. Auto type equals to this. Okay, and then I also need to store the fact that this has been unresolved, do I? Maybe I don't need to. Oh yeah, and this is a string, so maybe I'll use the string in that case. Yeah, okay. So say we try to find a type that's not there, we're going to return an unresolved type. Then at some point we're going to say, now that we found one, we're probably going to add a type. That's fine. But then what happens if we do actually add a type? It's in there, but it is an unresolved type. We need to this assert won't make sense anymore. Okay, so let's try this. We'll see if we find it in here. If we found it, let's just make sure that it is of type unresolved, and we're going to overwrite it with one that's not, or one that is actually. All right, it's a dynamic pointer cast, I think it's called, or stood dynamic pointer cast. If it's in the map, it must be an unresolved type. We will replace it either with another unresolved or with the actual type. Just thinking about if we parse multiple files, we might run into a problem where we parse a file where we define it, so it'll finally be replaced with the proper type. Then we parse another file where it's forward declared and so unresolved, and we replace it with that one, which would, oh no, that wouldn't happen because we would find the type. We would never add an unresolved again. Okay, so I think this is okay. All right, so let's just see if we did it this way, we should end up with some unresolved in our system. Right. Okay, let me put just a couple breakpoints in here. I want to see if we hit this, and I want to see us doing this thing. All right, so here we are. Type 28, it's that variable called next. So we are going to create an unresolved type and set the number 28 there into it and return that type for our pointer type. And then we will create an indirect type. So this, of course, is going to do the wrong thing, as I was saying before, and that's something I'm going to have to deal with later. So here, when I do this, this is just going to say star because the name of my indirect type isn't given a name. So that's, I'm probably going to have to change name to be a function like I said. But we move this type into there. So now we have this type that is unresolved. And then we're going to add this indirect type that points to an unresolved type. And this guy is going to add it, no problem. And then that gets added to our debug symbols. Okay, so no crashes so far. Oh, actually, there was something that didn't happen. Oh, interesting. It actually says next, and then we crash. That's fascinating. I guess it says next because next now points to something that's been unresolved. And then when we expand it, we don't handle it, so we crash right now. Okay. So what I did not see though is what happens when we're finished defining our type. Yeah, let me debug this again. What I expect is we're adding node star. That's our indirect type. So that was what we were seeing. Yes. So we're adding unresolved for this type here, 28. Type 28, as we look here, we're in the process of saying yes. You see, like where we have a pointer to a type that we don't know. So we're creating an unresolved type for 28 right now. But soon after, right here actually, we're going to create a type, an indirect type, for type 28. Or type 29. Oh no, sorry, that's true. We're creating a member here. So yeah, it's when node gets created. Where is that's for our struct. So let me see that. Oh, it's going to be here, the add struct type. So see, at this point, we come into lots of function calls. Type define is 28. So here we go and add 28. So, I mean, technically we could resolve in add type here as soon as we come in here, but I think I can actually wait to resolve until the very end when we're done parsing. I don't know if there's any need for us to resolve any time earlier. See, now we have an entry for type 28 in here. All right, so let's say we did that. So what we could do is maybe we could add a function here, and we'll call it like resolve types. We'll tell it that it takes a callback it returns a shared pointer given a string ID. I just have this idea of maybe how this could be done. Let's see. All right, so in this function, what we're going to do is we're going to go through everything we know that might have unresolved types. So basically everything that has types. So we know that, well, types will have types. Although I don't have, yeah, oh no, that's it. We're going to go through here. So let's start by that. So if we have, if I can write code properly, how does this work? Oh yeah, and I got to cast t like this. Then we call back our function. We'll call it the resolver. Indeed, instead of giving it I guess I could do that. UT ID. So my T here is a reference to the shared pointer in types here. So I think this would do the replacement here. And then the next thing to do would be to go through our functions and all their scopes. Okay, for each, no. Just a shared pointer of function. Oh, sorry, it's just a function. Actually, yeah, it is going to be scopes. So scope, because then the function has a scope. Oh, hey, Bama, how are you? Yeah, I'm alright. I'm doing alright. Can't complain. Yeah, I was just thinking scopes actually form a tree, so it's a little bit annoying. But I actually do have this traverse, so I can use that, I suppose. All right. All right, so we've got our shared pointer scope here. Oh, I made it for just const. Or maybe what I could do here is base my constants or the type on what I pass in. Yeah, this is not awesome. It would be better if I had a cleaner way to do this. But then I can go through its variables here. Or I'll call this root scope here maybe. And then we'll do like this, root scope, and then we can call this scope inside there, which I like a bit better. All right, and now I can do this thing again. All right, let's see if this actually compiles. Looks like it does. So, but basically what I'm doing here is I'm writing a function called resolve types, and the goal of this function is to go through all the data structures that I'm storing in the debug information that ultimately have a type pointer in them. And right now there's only two of them. Basically we have the list of all types here, and then we have in address to function a mapping of all functions. In each function we have a scope, a root scope, and then scopes can have children. So if we go up here to scope, so here's scope, So scope itself can have variables and it can have children, so child scopes. And the idea there is to go through the scope and all its child scopes and then go through all its variables, because variables have a type. And yeah, so that this way I can go through all the types, and basically as I traverse through all of them, if I find any that are unresolved, I ask them to be resolved via the resolver. And in fact, I should probably, let's do this here. The type should no longer be an unresolved type after it's been resolved. Okay. All right. The only downside to this method is every time I add stuff to debug symbols, I'm going to have to worry about whether or not types are involved. But let's see how that goes. And also, because now I'm iterating through everything, I won't do it every time we add a type. I will try to do it just once when it's all over. So at the end of parse, I suppose. Let me see. So here we'll say resolve types, and now I got to give it the resolver. So the resolver is, as we saw, a function that basically takes a string ID and returns a type. Let me see, where is it? And that did not quite copy that properly. Here we go. So Bama, you're asking, do you have often cases when your original software architecture what access, what for which functionality needs to be changed, and thus planning is key. What are your thoughts on this? Yes, I often have cases where I need to re-architect stuff. I mean, it's always happening. And I think that that's actually normal. I do think a little bit of planning is needed, but not too much planning. Yes, things do get more complex. I think the key really is there's kind of like a few basic rules I follow to try and help me get there, to keep things under control. So probably one of the most important rules in software engineering in general, I would say, is to not have any circular dependencies. If you can avoid circular dependencies, things will be just so much easier to manage. So like, I mean like at all levels, right? It's better to have a dependency tree than it is to have a dependency graph. You know what I mean? So types, if you have types that depend on other types, it'd be best if the second type does not depend on the first. The only exceptions I make for that are when the types are part of, let's say, the same module. Let's say in the same header file, and I have a couple of classes, they can know about each other. But outside of that, I really try to avoid it. And there are so many advantages to doing it that way. It really does do the thing of like, if you're really strict about it, you can create these kind of API layers, API walls between all your systems. And when you ask yourself, where should I put this thing? If you're fighting your system because you have to sort of like know about a type deeper, let's say deeper at a level deeper, you need to know about an outer type. You have to resist that urge to like grab that outer type and pass it in or something and think, okay, do I need to know about that type here? Or is it more like there's information in that type I should be passing down here? And in that case, maybe we need to pass that information down itself and not the type, Sometimes it means solving it by doing the dependency inversion. So like maybe type, you have type A and you have B, and A knows about B. And at one point you find that B needs to know about A, but really B just wants to know about part of A. So either you could just pass that in as variables, or perhaps extract out of A this new type C, and now A and B both know about C. And C becomes lower down the stack. You know what I mean? So like dependency inversion principle, that's actually a thing. The DIP comes up all the time, and it's part of keeping your types and your whole system basically all direction, like in one direction of dependencies. So if you follow that, like if you're religiously following it, you'll probably find your software easier to manage. One thing I did, and I try to follow that, and even I sometimes like will make mistakes there. Originally, when I wrote Vectrex, I didn't have like over here. You can see I have a bunch of static libraries, right? But originally, when I wrote this, because I was building it from scratch, it was just one big project, and just like all source files dumped into one big project. And although I was trying to be really careful about keeping dependencies in one direction, I actually had a couple of places where that was not the case. But it became really obvious when I started splitting up my code into libraries, especially, so like static libraries, you can have circular dependencies in them because of the fact that they're statically linked. However, I have a mode where I can compile my libraries as dynamic libraries, right? As DLLs, or shared objects, if you're on Linux. And when you do that, then you can't really have any more circular dependencies. Like you can't rely on the linker resolving a function call, say, that exists in a dependent, or dependee, or whatever you call it. Depender library. So that's one really interesting technique, is to try to maintain a build. First of all, split up your stuff into multiple libraries and see if you can maintain a shared object or dynamic library build. It's a really good way to make sure you're keeping everything in one direction. So in my case, you know, there is one direction. So Vectrex C is sort of like the root. It depends on, you know, everything. And I think you can actually see it here. If I go to, I don't think you can see it here actually. Oh, maybe here, references. There you go. So you see our references here. You can see Vectrex C depends on core, CPP DAP, debugger, emulator, engine, and Sdl Engine. Core actually depends on nothing. That's like, you know, at the very end. If I take, say, CPP DAP, that's not even my library, so it has no dependencies. Debugger, on the other hand, debugger depends on core, CPP DAP, and emulator. Emulator, if you follow that one, depends on core alone. I also have these things called engines, right? So let's say I take the Sdl engine here. So you can see Sdl engine it depends on many things, but let's see, it does not depend on, well, obviously on itself. So Vectrex C has everything, but then the next layer down is Sdl Engine, which has almost everything. And then that guy depends on, let's say, emulator, and also on engine, which is a place where I kind of keep things that are core to all engines. And then you can see there. So this stack is very, very clean. It's all in one direction, you know? And so that's, to me, that's probably the most important thing you can do. As for planning, you know, I'm really more of a fan of write code that you need and not code that you might need. I'm really, really big on that. I had this conversation recently with someone. I remember when I was young and I was first starting out, and I'd start writing code, and I'd start with my class interfaces. You know, I'd like write a class and a header, and I'd start thinking of all the functions I'd need and all the parameters they need. Sometimes I'd even start implementing them before I even had a use case for them. And that's a big mistake, because then as soon as I start writing code that actually needs them, I'd realize, oh, actually this interface doesn't make sense. Oh, I need to add another parameter. And then I just keep spinning my wheels and rewriting code I wrote before. So I prefer, you know, and I guess that's sort of like the test-driven way, which I'm not like a test-driven TDD like, you know, person. I don't do that generally, but I think that their idea is write the tests first, then write the code to fit the test. It's a little bit like that. I sort of write the code, not the tests, but like the implementation of what I'm doing. And as I'm doing it, I'm like, I need this to call a function that does this, and then I'll go and implement it. So that's my high level, you know, software engineering 101, how I do things. Hey, no problem, man. I'm happy to talk about these things. Okay, so let's see if this works. I'll put a breakpoint here. Okay, so now we're at a point where I think I'm probably doing a file here that's got like nothing. Yeah, so this is not going to do much. Just want to see it sort of step a little bit. Okay, so I've got nothing. All right, the next time we reach here, we definitely should have stuff. So let's see. About 21 types. In there, we should have an unresolved type somewhere in there. I should try to like make it easier to see these types here. It's annoying. All right, let me just put a breakpoint here. Otherwise, one over here. So no type in there. Does that make sense? That doesn't really make sense. Because we added an indirect type, didn't we? Oh, right. Types that points to types. Oh, that's annoying. Right. So maybe, yeah, I'm gonna have to do that. It's true. If I look at all my shared pointer types, let's see here. All right, I gotta go through my structs, my indirects, and my variables. Yeah, it's a little bit gross, I'm gonna admit. Yeah, this sucks. I gotta find a better way. Oops. Yeah, this doesn't feel like a great solution. I gotta come up with something a bit more intelligent. I think I'm gonna have to do something whereby I do track the members. Don't know. But let me just finish this, because when I have a working solution, maybe I can use that to like inspire something better. So let's say this is an indirect type. I got to go through all the members for my struct type. Now, of course, that itself might be another type, so I actually need to call this code recursively. That's what this means. Yeah. Now, if I recall, you cannot do a recursive call on a lambda. So what's the trick again? Oh yeah. Yeah, the trick is to use a std function for it. And basically you say something like this. Like that. Okay. I think that should do it. Whoops. Okay, so here we go. We're going to try to resolve. Huh. It's not letting me. Here we go. Put a breakpoint right there, see if we ever hit that. Oh, here's our add struct type. Okay. Find type. Okay, so now I think it should do the thing. So what was I parsing before when I hit this? Parsing main now. Okay. So we have 46 types. So let's just see what happens. At one point, there we go. So we finally find an unresolved type. T here. And it's going to be tough to see if this actually worked. I've got a reference here. it's very important that I have references all the way down. So this is the type here. So let's see, what have I got? Got our indirect type. So that's our pointer that we were talking about earlier. That has the wrong name right now, but fair enough. And we can see that it's type 28, which corresponds with this type here, meaning it's a pointer to type 28. So now what it's going to do is it's going to do a resolve, and it should get back the struct node as the actual indirect type. But the current type that it has is this unresolved type right here. This should be replaced. So let's see what happens here. We're going to go and call our resolver. Resolve. And here is our resolver. We're going to look for type 28 in here. And of course it should be in there. There it is. It is a struct type called node. Perfect. So we return that. Get back out of all this stuff here. So there's T. So here's our assertion that it is not an unresolved type, which is good. And then we're going to replace T here. And if I just go up the stack, there we go. There we go, struct type. So that actually worked. And then we got an exception. Oh, so close. Stack Overflow. What did I do? Oh, I must, okay. My recursion is not ending. Okay, yeah. Why? Why is this happening? Oh, okay, it's while we're going through members. Why would this cause a problem? Let's see, next. Indirect type. Okay. It is an indirect type, so we're trying to do a resolve on it. Hello? Oh, okay. Oh, right. Oh, that's funny. Because it's self-referential. It is actually recursively defined. That's amazing. You see, like, basically, so we're going through and we've got struct node and we're going through its types, and we see that next has a type that's undefined, like a unresolved, right? So we're like, okay, let's resolve it. And when we do, we see that the type that we do have is it's a pointer to an unresolved. So sorry, we say, okay, process each type. So we process next. It says, okay, next is a pointer, an indirect type. That indirect type, it currently points to a type that's unresolved. So we say, okay, so resolve it up here. So from here to then asking it to resolve. And so it says, okay, let me resolve that one. But actually, hold on. I was just going to say the type we're trying to resolve is itself node, but still, it should have still worked. Why is it so slow? Wow, it's like crazy slow. Actually, that doesn't make sense. It should have gone into unresolved type, actually. So we replace it with struct type when we resolved it. So then what? Is it on our way out? My feeling is it's really slow because it's got just so much, like such a huge call stack, so maybe that's causing Visual Studio to be crazy slow right now. Oh, I see. So we replace it with a struct type, and then we end up going through all the types and trying to resolve them again. And that's where we have the recursion. Yeah, so okay, so that's what's happening. We basically resolved our next pointer to a type that is itself a node, and then we keep asking to resolve it, and then it goes over and over and over, basically on the same struct. So I need to avoid this recursion. The only thing that I don't get here is, yeah, how am I going to do this? How do I avoid this recursion? I can't check if the type I'm about to go on is the same type as myself because, you know, we could have, let's say, A depends on B, depends on A. So I won't be able to know that. I'd have to sort of remember the types I've visited so far and avoid revisiting the ones that I've seen, which is a bit crappy. Unless there's another way we can go about it. Maybe I can collect the ones I'm going to resolve and then flatten at the very end after I've visited everything. Maybe. Maybe. But that's really a shame. It'll make this a lot more complex, that's for sure. Yeah, this is annoying. Trying to think of all kinds of ways I can break this recursion, but in an elegant fashion that's not expensive either, and not make the code complex. I have no choice but to go through the types this way if I'm going to iterate over everything. Maybe this is more proof that this is not a great strategy. Okay, how about this? I'll try a slightly different approach. So what we'll do is we're going to recurse through everything. We will collect and all types we find along with the pointer to the shared pointer that we need to modify. That's sort of what I was thinking before, sort of like the flatten. So we collect all like the type, the shared pointers to type that currently are pointing to something that's unresolved. And then we go through that as a simple linear vector, and then we ask to resolve those. So we collect the unresolved shared pointers. Something like that. So I'm imagining something like this. Okay, so if it is an unresolved type, in fact, I suppose I could store as the pointer to shared pointer. It will now, if I dereference it, be pointing to an unresolved type. Fine. So let me see here. It would be something like this. This becomes try, resolve, recurse. We'll make a try, resolve. Okay, well, first I will need to do another dynamic cast here. Okay, so let's see, does this make sense? We go through, we call try, resolve. Right now I'm just gonna make this a variable at access just to see if this works. So I clear the array, we call the try, resolve, recurse, which goes through, and every time it finds an unresolved type, it pushes back the address of that shared pointer. So this is the address of the shared pointer that we need to replace. And then once we're done recursing, we go, if we have anything in there, we go through and we replace, I don't know if this is going to work, but we go and we replace that shared pointer. Oh, let's see what happens. All right. I'm going to try and make this a bit more clear. I will clean this up. I just want to see if this even works. Okay. Whoops. Where are we? Oh, looks like we have 1 to resolve, which is what we expect. What is our pointer to pointer pointing to right now? Okay, so it's pointing to an unresolved type. So my question is if I have a pointer to a shared pointer like this, yeah, I am going to be replacing that specific reference to it, I think. So this might actually work. All right, and that's that. Oh, and then we've got another, this time for something else. Oh no, same problem? Oh, okay, because the next time I go through, this is gonna happen. I see, so the moment I've resolved something like this, the next time I try to resolve it, this will go wrong. And this is gonna keep happening over and over. Yeah. Unless I guarantee that I only do this kind of resolve as the very, very, very last thing I do. Oh, yeah. The fact that this is hard makes me feel like either it's just because it's a hard problem, which it is, but maybe it's not the right solution. I was hoping that I could make this simple by creating these unresolved types and resolving them later, but the way I'm doing it is not easy enough. Let me see something. What if we did this? I just want to see it sort of work. I think if I wait till I'm done collecting everything. Let's see. So I was afraid I would collect multiple times the same thing to resolve. Just let's try with a set, so I don't get the multiple entries there. Okay, so I didn't get a crash this time. So let's see what this looks like here. Looks like it actually worked. So see, like N1 points to Yeah, I should put values in there. It's not very useful. Okay, let's put some values. Let's see here. Hard problem for sure. Yeah, thanks, Bama. I think so too. So let's see. Did it not initialize correctly? Oh wait, it did not compile correctly. What did I do here? That's better. Should pay attention. It wasn't actually built properly. To avoid recursivity, yeah, for sure. But you know, when dealing with trees, I mean, the way to avoid it is you could use recursion to flatten out your tree, and then that's pretty much what I'm doing. But yeah, I'm sure I'll come up with a better technique here. All right, so n1 is 1, and its next points to. It's interesting. It actually says star next. I didn't expect that. It points to v2, and which points to v3, and then this next is null. Unfortunately, I can expand null pointers, just because. But hey, Lord Alpaca, I do have Vectrex Roms to test my stuff with. Turns out that the Vectrex after it went out of business, the company there that made it, the GCE, they actually made all the games they made, which is not that many actually, but they made all of it, including all the information for the Vectrex public domain. So they're cartridges actually, yeah, they're totally cartridges. I have my vector. I should totally bring it down and show it again on stream. I did it a long time ago, and I could show you the cartridges and how all that looks. Obviously, it's a one Google search away, of course. It looks like that. Well, I mean, you can get the ROMs from the cartridges. I mean, I just get them from downloading them. But you know, if you take a cart and you desolder this chip and you pop it into one of these, you can actually see a picture of it here, into one of these programmers. I actually own one of these. I've programmed actually, you know, my game that I made, I've been using as a test, this Vectrex Pong. I've burnt it onto one of these chips and put it onto one of these carts here and popped it into my Vectrex, and it works. Yeah, exactly. But yeah, you can totally read them. People have done it, so that's how they've dumped the ROMs. And yeah, you can just download them. And if you download my emulator, it comes basically with the ROMs. It comes with a bunch of ROMs that are open, like public domain. So like if you have Windows or Linux, you get this zip file. And in there, you'll see under Data ROMs, there's a nice little selection here. No, there's no real copy protection. There's almost nothing really. It does like this. It does some slight like, you know, it's not copy protection. It does validate that the header in the program contains certain characters. It's like nothing. Yeah, it's really cool. Basically, have you ever seen like it's all lines? Yeah, pretty much. You know, you can do raster the way raster is actually done, which is you move the beam, you know, horizontally across, turning on and off the beam, and that's how they do like font rendering. And then the rest is, yeah, you're just moving the beam around. The whole API is you taking the beam and you know, sending it into different directions. Yeah, actually, it's funny you say that. Like I had never really thought of it like logo until the last stream, and I was, or maybe it's 2 streams ago, I don't know. I was talking about it and I was like, yeah, it's kind of like logo, you know. You think of it, you can think of it that way. I mean, there's not like the idea of setting an orientation and moving forward, but it's more like, you just think of it more like setting an XY target location, setting a speed, and allowing the beam to get there. What's really tricky though is that, you know, you don't really know when the beam is there. So, because, you know, it's really analog, right? And so programs, and there's an abstraction, like the Vectrex has this like BIOS that's built in with a whole bunch of useful functions, and if you tell it, I'd like to draw a line to this place, it knows like generally how many cycles that's going to take, and so it actually has like a little loop where it waits with knops in there and all that, just to like make sure to eat up about as many cycles as is needed to make sure that the beam got to the target location. And then you can do, you know, then it'll return from the function. But it actually is conservative, so you actually lose some cycles in certain situations, and there are people who have rewritten their own routines for moving the beam around, because you only have about 30,000 cycles per so-called frame, and so people, you know, to try to push more out of the Vectrex, some people have written their own routines for that purpose, to make it as tight as possible so it's not wasting cycles. Yeah, I know about the turtle module. Yeah, it's some pretty cool stuff. I learned on Logo. That was pretty much my first programming language, although I didn't know I didn't think of it like that when I started. It was just something I did in grade school, and I loved it, but I had no idea it was programming. It was kind of like 20 years later, I was like, oh yeah, that was programming. At the time, it was just playing on the computer, you know what I mean? So I'm totally like, I'm happy this is working. I'm a bit baffled by the fact that it says star next here. I don't understand how that happened. Let me just take a look. When I resolve the type, it should be obvious here. Okay, nothing to resolve, nothing to resolve. I have 1 to resolve here. And let me take a look at this. So my name is empty quotes. So no, it's not obvious. Let me see here. Try that again. So here, so here's my indirect types. This is the one I wanted to look at. See, the name is just star here. But we saw star next. How could that change? Let's keep, whoops, that's not what I meant. Let's keep this exact pointer in memory here. So this is the indirect type that we're about to fix up at the bottom. Yeah, we're going to try and insert it a few times. So here, when we go to resolve it, see, we changed the type here to the struct type, but you see the name is still star here. Wait. Yeah, that's it. See, it says star next. I don't understand. It's like what I want, but I just don't understand how this happens. Oh, wait. Could it be that what's happening is that I parse it again later, and then this time I find the type? Does that make sense? Not really. I'm like not sure what's going on. How this is it's like great, but I'm sure that it's relying on some behavior that doesn't make sense. That like I can't rely on. Let me see. And look for. Oh, here. Okay, the variable name is fixed. It's the type name that's going to be wrong. I see. Okay, so actually, so we should see the type name as being incorrect in here. Let me see. It's just because we don't really display the type names until you hover. Ah, there it is. There's the star, the asterisk. And then the type of this is node, which is good. But then the type of next is just should be asterisk node. That's what it should be. Okay. The variable name is correct because that happens dynamically, but the type name is done statically while I'm parsing. So, thoughts on this. So what I've done so far is I created a new, where is it? RST debug symbols here. So I created a new type called unresolved type, which holds an ID. And then as we're parsing, whenever we see a type we don't know, rather than, do nothing, we create this unresolved type, and then we just keep going. Then at the very end, I do a resolve of all types. So resolve types, which is a function here, and I pass it a function called a resolver. Oh, sorry, I missed what you wrote, Lord Alpaca. You said for debugging trees, sometimes I use graphviz, or graphs rather. Yeah. True. That's not something I think would be useful to me right now, just because it's not very complex, my graph. But I've definitely used graphviz for problems that larger graphs and stuff. This is a pretty simple. It's more of a simple tree. Yeah, I'm keeping my examples simple so that I can build on these. My problem here is more of a software engineering problem. So then what I've done is I've written this function, which has gotten a little bit complex, but the idea there is that to go through all the debug info where I store types. So right now I have one vector of types here. So I just go through them and try to resolve them. Apart from that, this is a little bit more complex. I have this mapping of address to functions, and every function has a scope, and every scope is actually like a tree. So I go traversing the scope of each function, and for each one of those, in each scope, there are potentially variables, and variables themselves have types. And so this basically covers all types. And as I go through there, I say try to resolve. Now types themselves form a tree, right? So if we go back to here, to my type, all my types, they're all here on screen here. So you can see I have this base type, but you have a primitive type, which is just a regular type. So there's nothing to resolve for that. Same thing for a noon type here. But the kind of inner node types, like struct type. A struct type is made up of members, and members have to have a type here. Each member has its own type. And similarly, indirect type, which are like pointers and references, that's a type that has itself a type member, because this would be, let's say, a pointer to this type. So effectively what I'm doing is then to resolve a type, I have to actually recurse, because if it is a struct type, then I need to go through each one of its members and then resolve that type. And then that type itself could be, let's say, another struct or another indirect type or whatever. The thing goes on and on and on. So what I do is I go and try resolve here. And try resolve actually calls this try resolve recurse right now, where I collect into an unordered set I collect into this unordered set of shared pointer star, so pointer to pointers, all the types I find that need to be resolved. So I'm looking for unresolved types in there, and I add them to my set. So, you know, if I have, let's say, somewhere, if I have a variable somewhere that, you know, let's go back here. If I have a variable with a type, and that type is a struct, and one of those struct's members is a type to an unresolved, I'm going to have the pointer to that specific instance in my set. So when I'm all done recursing and collecting, the final pass here is to go through this set and actually resolve. So overwrite the shared pointer that pointed to an unresolved type now with a new type that is the resolved version. And I do that by using the ID and calling the resolver function that was passed in. So that's sort of the idea here. I don't think it's crazy. Some of the downsides to this, apart from it being a little bit complex, is that I think if I were to... What are some of the downsides? Well, okay, one of the downsides is that as I continue to build up my debug symbol types here, I have to always remember if I add another inner type. So for example, I know one that's coming is going to be a union type. So unions are actually made up of multiple. The unions are very similar to structs. But yeah, a union is going to look a lot like a struct. It's going to be a vector of members. The only difference between a union and a struct is that all the members of a union overlay in memory. You know. Oh yeah, that's pretty much it. In fact, I may actually end up using this type and maybe making a common base or something. We'll see. But the point is that if I add that, then I got to go in here and make sure I have to remember to like extend, you know, this code here to like catch the types that have to be extended. So that's the one thing that I'm not a huge fan of. I could maybe fix that problem. So one way I could fix that is to like have type here have some kind of virtual function that allows you to visit all the types. You know what I mean? And then, you know, implement it, let's say in struct type, to visit all the types of its members. In indirect type, it would just simply visit this one. And then that way I could, you know, get rid of the dynamic casts and just say like, I just got types and I'm just gonna traverse my types. That actually might not be a bad idea. It's more the sort of the object-oriented approach to to going through all of this. So that I guess would simplify things. And then when I add a type, I guess I could see right there, oh, does this type need to implement this type visitor, you know? So that's interesting. So build a recursion into the type system. Or the type visitation into the type system. Like if we acknowledge that type forms a tree, we can put that in there, and yeah, maybe I'll do that. So that'll definitely simplify this code because I won't have any dynamic casting to do in here. And then the other thing I was thinking is that right now I'm parsing RST files. These are the listing files one at a time. And as I do this, I continuously collect more and more data types. And if I'm resolving after each one, there's a little bit of a waste there of retraversing all the types. But there's another concern of mine, which is the problem of, let's say I have a header that forward declares a type. And let's say 2 CPPs that include that header. And in one of them, I resolve the type. If I process the one that resolves the type first, suppose that's okay. Then when I parse the next one, it'll know about the type. If I process the header that has the unresolved type, it's only forward declared and remains unresolved in that CPP, and then start parsing the next one, it'll see the same type. So I don't think I handle yet in my RST parser what to do with like duplicate types, but I got to be really careful not to, yeah, that was my concern, is let's say like not to ever overwrite a type that's already been predefined from another compilation unit. So there's a little bit of concern there, but I think it should be okay. The other question I had is, why did I need to do the set again? I ended up having 5 times the same shared pointer that was found by my recursive try resolve function here. Why is that? Oh yes, I remember what was my concern before. About having multiple resolves between each stage is that, yeah, it would be a problem. So let's say we're parsing a CPP file. We have a recursive definition, right? Like this one. We resolved it, and then the next time we parse, when we try to resolve something that's already been resolved, we're going to end up in a recursive situation again, because now this type is resolved, and it's just going to keep trying to resolve a type that it knows about over and over and over. So in fact, it's easy to prove. All I got to do is call, yeah, it's going to be easy to break this. All I have to do is come here. Where is it? RST parser. Call this twice. Okay, the first time it's fine. Second time it's fine. The third time we're going to go in here. So now what I suspect is this next time here we're going to end up with I believe we're going to end up with a Stack Overflow. And there you go. Or something like it. Yeah, there you go. There's our Stack Overflow. And it's because when I'm visiting my type tree, I have a recursive type definition. So I don't know to stop recursing. So maybe ultimately I do need to track types I've already visited to avoid revisiting them. If I do that, then it's okay to call it multiple times. The only other solution, of course, is not to call this function twice, which is doable. The way to do that, right now I'm calling this, so because I'm trying to do it in the bottom of parse, but we call parse, what do we call parse again? I think it's in, wow, that's not useful at all. Let's see, what am I looking for? RST. Debugger. No. Where do I construct an RST parser again? In the DAP debugger, okay. So like here, so I do this thing where I parse the RSTs. I would have to create the RST parser once, parse all of them, and then at the end do some kind of like resolve on it or finalize or something like that. That would be, you know, one way to make sure to only call the resolution once. But I'm not a huge fan of that idea. So maybe it would be cleaner to make sure that I can traverse this recursive definition thing. The only thing is it's not going to be like well, I suppose if I give each type a unique ID, like an incrementing integer, then probably, you know, I could easily look for whether I've ever visited this type. It's because I don't have an easy way to hash these right now. I suppose I could use like the address of the type or something like that. Yeah, I suppose I could do that. And if I did that, then I wouldn't have to do the flattening that I'm doing here. I could keep it like the way I had it before. Let's see. Actually, I'll do a get. What do I want? Do I want the address of the shared pointer, or do I want the address of the thing it points to? All right, let's just do this. If I've seen it, return Does that work? We are about to visit it, so say we've seen it. Yeah, I think that would work. so let's go back to, in that case, don't need most of this. Don't need this here. What did I do? Okay, so let's see what happens. Okay, so there we go. We've got a visited types for T. The only thing is, this happened even before we were asked to resolve. So what does that mean? What is my T? Oh, it's a primitive type. Actually, this might make it go faster. I'll avoid trying to resolve types that have already been resolved, strangely. I say strangely because I didn't think this would make it faster, but it might actually do so. Struct type. So this is the type that has the two members. Oh no, this is another type. Okay. So there's our resolve. And now our type is the one with next. So now we're going to skip this because it's already been resolved. Let's see. Indirect type. To the struct type. Okay, so this has been resolved. So I think actually we should be good to go. And then this next resolve does not crash anymore. So actually it turned out to be not so difficult to do it that way. Well, I should have just done that at the beginning. Avoiding recursion. Sometimes the simplest approach is the way to go, isn't it? So this solves the problem of, well, it behaves exactly like before actually. It doesn't solve my problem of the type name for next here, but that's a separate issue. Not too bad. Yeah, I think I prefer this. It definitely simplifies the code. We must make sure not to traverse next. hopefully this comment will remind me enough of what this is all about. Okay, so yeah, I'm gonna have to stop here because it's late. All that I was gonna do next was start thinking about trying to solve the problem of the name, which is again it's a general problem. It's like anything in my type system that where is it? Here, anything in my type tree here that gets set based off of the type of something else will be a problem. In this case, indirect type, its name is star the name of the type. So probably what I should do is replace this with functions. Like that's what I was saying earlier. But that's a bit unfortunate. The only other thing I could do is like some kind of post resolve, you know? If I've resolved a type and then tell the type, hey, you just got resolved, you know? Your type just got resolved. So like indirect type would say, oh, okay, you've resolved my type, then let me reset my name or set my name. Yeah. Not amazing, but, and it's probably not going to be the only time I'm going to have this deal here. Yes, bonne nuit. Take care, Bama. As a bit of a hack, I suppose I could do it like this. I really don't like it, but say I return bool here, and make it so that if I resolve something, I return true. I guess I can move this down here. Then I could do the total hack. Need a more generic solution for post-resolve fix-ups. But still, it is the only one I know of right now, and maybe, you know, maybe localizing fix-ups into the resolve types function might be manageable. We'll see. Like I was saying before, like if I do something where I recurse over types without dynamic casting, maybe there it'll sort of move the, if I'm doing visitation, maybe that's where this kind of code will move, and it'll move into the type itself. So indirect type would have some kind of, you know, type visitor in there, and it'll maybe be able to do this code there. But let's see. So let's see now. Now, see, now it says, oh, actually, was it is it node star? No, oh, what did I want to put again? It's not, oh, it's not, I don't remember. What do I normally do? It's node star, right? It's not star node, it's node star, yeah. Of course. St parser. Yeah, okay, the type name plus the asterisk, of course. Getting confused with the variable name there. So the other way around. Because what I don't like too is the fact that I'm doing this in two places, you know? Gotta stop the debugger. So n is a node, v is an int, and next is a node star. And then what it points to is a node. So yeah, there we go. So yeah, not the most elegant solution, but you know what? It works. It works. Yeah, and you know what? It's not so bad, I think. So given that, I think, now I know like the forward declaration example won't work right off the bat, but I'm just curious. If I compile this and then I manually edit this, just because I know I don't match this part properly there. So if I just remove that part, I'll have to obviously fix my code to handle that when defining pointer types. But let's say it's like this. This is another one of those where now the resolution will occur later. So this will be, it'll create a pointer called for forward, and then it'll resolve later when it sees this type. So I'm just curious to see if this works. Now to see if this works, we're going to need a bar here. And a forward. Okay, actually, let me remove this again. Yeah, let's try. So no crash there. It actually works. There you go. Forward star. Forward 46 minus 3, which were the values we saw over here. So yeah, this totally works. I just need to handle the parsing of the forward declared type there, basically to ignore it. I don't think I need that information. And then I've covered forward declared types, it seems. So yeah, that's pretty neat. All right, this is a good time for me to sign off. So guys, thanks for watching, and I shall see you next week on Tuesday. So take care.